In this session, we will have a brief introduction of key techniques used in speech codec designing and the performance evaluation of speech codecs. There are some key techniques mostly used in speech coding, such as short-time analysis of speech signal, pitch estimation, linear prediction, vector quantization, ABS, analysis by synthesis, perceptual weighting, post-processing, and so on. The techniques ABS and perceptual weighting have been used in CALP-based codec, the scheme of which have been introduced in last session. For speech coding, there are some special improvements to enhance the performance. Some speech coding standards like G.729, G.723.1, and AMR use the methods of open loop and closed loop search to estimate pitch. The accuracy of pitch searching directly affects the quality and efficiency of speech coding. Most of the open loop pitch search method uses the weighted correlation function CD based on perceptual weighted speech SWM, so as to obtain the optimal open loop pitch delay. The weighting function WD emphasizes lower pitch values, reducing the likelihood of selecting a multiple of the correct pitch delay. Open loop pitch analysis is performed in order to simplify the pitch analysis and confine the closed loop pitch search to a small number of values around the open loop estimate pitch values. The so-called closed loop search is a fine estimation in the range of pitch period obtained by open loop estimation. The closed loop search is completed in the process of adaptive codebook search to estimate the pitch value from the weighted input speech and the long-term filter state. The adaptive codebook search generates the pitch delay and gain of the pitch filter. In the closed loop search, the pitch is searched using error minimization loop analysis by synthesis on a subframe basis. Once the optimum integer pitch delay is determined, the fractional pitch search is performed by interpolating the normalized correlation searching for its maxima. Linear prediction analysis hands some operation details in speech codec. In order to reduce the error introduced by the truncation at both ends of the window, abrupt rectangular windows are generally not used, while windows with smooth transition characteristics at both ends, such as hemi-windows, are used. In order to avoid discontinuities between frames, LP analysis window length is greater than the speech frame length, and there is overlap between adjacent analysis windows. Before LP analysis, a pre-emphasis processing is firstly used to strengthen the high-frequency formats in the speech spectrum, making the short-time spectrum flatter. Pre-emphasis is a kind of high-pass filter aiming to improve the accuracy of spectral parameter estimation at the encoder, and a corresponding de-emphasis processing should be done at the decoder. In the LP analysis of AMR codec, The autocorrelations of windowed speech are converted to the LPC coefficients using Levin-Dobin algorithm. Then, the LPC coefficients are transformed to the linear spectral pair LSP domain for quantization and interpolation purpose. LP parameters are smoothed between frames to avoid discontinuity by interpolation on the subframe basis. The interpolated LSP parameters are converted back to the LP filter coefficients to construct the synthesis signal at each subframe. The scalar quantization method, uniform PCM, is often used to quantize pitch values, which need to be accurately quantified to keep good synthesized speech quality. For 8 kHz sampling rate, the typical pitch prediction range is between 54 and 400 Hz, corresponding to 20 to 147 samples. That is 2.5 to 18.375 milliseconds. We can use SAM-based PCM coding. We usually use additional bits to encode the fractional delay of pitch period. Differential quantization is often used to quantize continuous sample amplitudes and energy gain parameters in pitch cycles or subframes which have high correlation between neighboring parameters. The single set of LP parameters is converted to linear spectral pairs LSP and vector quantized using split vector quantization SVQ. Split quantization divides the vector into several subvectors and quantizes each subvector. Matrix quantization can also be used to take advantage of the correlation between these subvectors in continuous time frames. Sometimes, first-order moving average MA prediction is used to remove the redundancy of LSP between frames. There are some test indicators to evaluate the performance of speech codec, such as coding rate, speech quality, delay, and complexity. If the restricted speech quality can be guaranteed, the coding rate directly reflects the compression degree of speech information. The coding rate can be measured by bits per second, BPS, which represents the total rate of coding, or bit per sample, which represents the average number of bits used to encode to each sample point. Obviously, under the same synthesized speech quality, the smaller the index, the better the codec efficiency. For variable rate speech coding algorithms, the coding rate usually refers to the average coding rate of all speech frames or only active speech frames. The lower the average code rate, the greater the overall speech compression. The quality of a reconstructed speech after coding is a key index to evaluate the quality of speech coding algorithm. There are two main methods to evaluate speech quality: objective evaluation and subjective evaluation. Objective quality assessment measures the distortion of speech signal using some objective indexes or standards, such as segmental SNR, SEG-SNR, perceptual SEG-SNR, PSNR, Septural distortion measurement SDM, PSQ, POLQA, and so on. Subjective quality assessment is currently known as a more accurate method. It is to select the appropriate listeners to evaluate the reconstruction speech. Divide the quality level according to a certain predetermined scale, and count all the evaluation results to get the index respecting the subjective quality of reconstructed speech. The most commonly used subjective quality test method is MOS, mean opinion score. Excessive delay will affect mutual understanding of two-way communication. For example, the delay above 150 milliseconds is not acceptable for high-quality interactive communication. The delay of speech codec is a sum of different types of delay. Algorithm delay refers to the time needed to accumulate one-frame samples before processing. In addition to the speech frame to be encoded current frame, sometimes the processing needs look-ahead data, that is, the length of speech block processed ahead. Computational delay is the time for speech codec to process speech frame. For real-time operations, the computation delay must be less than the algorithm delay. Algorithm complexity usually refers to the amount of computation and memory consumption related to hardware implementation. The number of addition and multiplication operations can be used to roughly compare the algorithm complexity. The calculated amount can be measured by operation time, operation number, WMOPS, number of instructions, MIPS, which is hardware related, and so on. While the storage space can be measured by RAM size required to store algorithm variables, ROM size required to store algorithm instructions and constants. In general, the complexity of encoder and decoder is required to be as low as possible in interactive real-time communication. The complexity of decoder is required to be less than that of encoder in non-interactive applications, such as broadcast and streaming media. That's all for this chapter. See you next chapter.